Hello everyone. Welcome to the ninth week of interaction session on the course on robotics basics and selected advanced concepts. So, just an introduction. My name is Soumya, and I am a PhD student at IIT Gandhinagar. I am your TA for this course, and this is the ninth week we are into. Last time we saw many problems. So initially we discussed the concepts, and then we solved many problems on dynamics of serial and parallel robots. So before that we were only dealing with kinematics and singularity and velocity and static analysis of manipulators also we did. Then we moved to redundancy, and finally we looked at dynamics of serial and parallel robot. Now, when you know the kinematics and dynamics of the robots, be it serial or parallel, you need to control it. Like you have some desired reference to which you want to reach, and how do you reach that reference? How do you maintain that reference? How do you minimize the steady state error? How do you reach faster, or how do you dampen the oscillations when you reach there? So all of these things are part of control. Apart from that, you also do motion planning. For example, if there is a trajectory and there are some waypoints given, for example, if it is of this sort, and these are the waypoints by which the manipulator has to pass through, then how do you plan the motion? Okay, how do you travel in between both of these waypoints? Is it this trajectory that you're going to take, or it is going to be something else? So there is something called trajectory planning. So we are going to see all of those today. So the lecture will start with basics on motion planning, and then we'll see how do we control a single link and how do we control a multi-link serial manipulator. Then we'll have a couple of questions, and after solving the questions, I hope this would be very clear to you, and it will also help you in solving your assignments, right? So since we are into 9 weeks, and after this we just have 3 weeks left, so this lecture is very important because it deals with linear control of robots. There are a few challenges when we do linear control. For example, if our system is completely non-linear, it is not a linear system, or let's say there are some factors which we have not already considered. There are non-linearities in the system, there are some uncertainties in the system, or the model that you're having of the robot is a linear model, but actually it does not always behave linearly. For example, you might have seen the spring does not always behave linearly, the simple pendulum does not always behave linearly. It is within a different within a band, but the linearity is not always there, right? So what if we want to do non-linear control of robots? So that is something that we'll see the next week, and then we'll have wheeled mobile robots. That would be again switching the gears completely, because from the manipulators you will move to the wheeled mobile robots, and then we'll see over constraint mechanism and so on. So these are the 3 weeks left right after today's session. So in case you have any questions, then you're free to ask, and please clarify all your doubts before the exam starts. So we'll meet for 3 more times after this only. So it would be good if everyone attends and uh, watches the lecture. As of now, just one student is present. It would be good. So I think this would be a recorded lecture and it would be uploaded. So anyone who is seeing the lecture, please attend the sessions because it is for your benefit. You get to study a lot of things. You get to understand a lot of things. It is very important. All right. And Shravan, are you there? May I know, today was the session which was scheduled with Professor Ashitava Ghoshal? Like you had some interaction session, right? Okay, but can you tell me what all was covered? Like, was it a doubt solving session? No, no, I'm not asking about the last class. I was asking about just Professor Ashitawa lecture. Not lecture actually, whatever. I think in the session, if you were present, that's okay. Okay. So I think that is a really good thing that professor himself is interacting with you. In rare courses, I have seen this happening that once a professor has got or has scheduled a course on NPTEL, he comes and interacts. But it is very nice of him that he came here and he interacts with all of you. He tries to understand what is going on and all of those. So I think this was the second live session. If there are any other sessions, you everyone should attend because it is really good for you. Okay. Okay, so let's start with today's task. So we'll start with motion planning. Okay, and then later part we'll see controls. Apart from the lecture, I'll bring some element of control from my side also, because control is a whole subject. It cannot be taught in a single lecture. Okay, so since this is robotics course, obviously you can't dedicate many lectures to control, but control has its own like way of doing things and everything. So that is a good thing that you should learn. Every roboticist should know that. Okay. Okay, so let's start with today's lecture. So today we'll understand two very important aspects of robotics, right? And what are they? One is motion planning, and the other is control, right? So when we are doing this, we should start with trajectory. Okay, so what is a trajectory? It is basically a time history of position, velocity, and acceleration of robot joints or end effector. Okay, so position basically tells you where the robot is, velocity tells you how fast it moves, and acceleration tells you how smoothly it moves. Okay, so uh, if we talk about trajectory planning, what it is? So if we talk about trajectory of a robot manipulator, we have different algorithms for planning and generation of trajectory, right? So when we want to define what should be the position of the end effector, or what should be the velocity of the end effector, or acceleration of the end effector, we basically want to plan all of these things, and then we have a number of algorithms. Okay, so the main issues that incur here are what it's not really easy and flexible to plan, and the planned trajectories must be sufficiently smooth, so there shouldn't be a jerky motion, and there should be efficient representation of trajectory in a computer and generation of desired trajectory in real time, right? What is happening in hardware should also comply with what is happening in software. Like there shouldn't be much error difference, otherwise that itself causes a lot of error, and you do not move to the desired through a desired planned trajectory. Okay, so real time computation is really a problem, flexibility is really a problem, and we want it to be smooth, we want to avoid any kind of jerks. So in robotics, we don't just care about reaching a point, we care about how we reach it, and that is important. Is something that we care about, and not just about how we are just reaching it. Okay, so there are two types of trajectory planning. One is joint space, and the second is Cartesian space. Right, so what do we do in joint space? We plan theta 1, theta 2, etc. And what do we do in Cartesian space? We actually plan x, y, z. Okay, so we do all of these things. Now there is a requirement of continuity. Okay, so C0 means position continuous, C1 means velocity continuous, and C2 means acceleration continuous. Right. So robots at least require C2 continuity to avoid vibrations. Okay. Now let's start with joint space trajectory. Okay. So what do we want? We want theta t naught to be equal to theta naught, and theta at final time to be equal to theta f. Okay, so the first method that we can use, if we want we just want these conditions to be met, so the first method that we can use is linear interpolation. Right, so what we can do, we can write theta at some point of time is theta final minus theta naught upon tf minus t naught, which is basically the slope. This is just writing the equation of the line, right? So what happens here when we try to get equation by linearly interpolating the points in between? What do we get? What is the problem with this? The problems are velocity is discontinuous, right? Acceleration is undefined. Sorry. So this causes jerks and it is bad for actuators. Okay. Second method that we use is piecewise linear. Okay, means we divide into segments. Okay, and we switch between these segments. So what happens? The velocity changes abruptly. Okay, so it is not even C1 continuous. So this is really bad. Okay, so what method do we use then? Both of these methods do not work, right? So we move to cubic polynomial. Okay, so we assume that theta t is some cubic polynomial, a0 plus a1t plus a2t square plus a3t cube. Okay, and there are a few boundary conditions. This is just assumption. Then there are boundary conditions, which are theta t naught is equal to theta naught, theta tf is equal to theta f, theta dot t naught is equal to, because we want to also bound the velocities, we cannot have any velocity coming up, right? So it's theta naught dot, and theta at final point of time is theta dot f. Okay, so what do we do? How do we do this? Let's say our t naught is 0. Okay, we are starting at time is equal to 0. Then the step 1 is to calculate theta 0, what it would be? It is theta naught, and that is equal to a naught, right? Because if you put here t is equal to 0, you'll get it equal to a naught. Okay, then the second step is theta naught 0 also we need to find out, and what it is, again if you find it out, it would be a1, which is, because you have to differentiate it, right? It is theta t. अगर इसको differentiate करेंगे, what we'll get a1 plus a2 t plus 3a3 t square, right? So it would be a1, which would be equal to theta naught dot. Okay, now step 3, as at t is equal to tf will take. So we'll substitute the equation. Theta f is equal to a naught plus a1 tf plus a2 tf square plus a3 tf cube, right? And here if we substitute the value of a naught and a1, it would come out to be theta naught just a second. Okay, let's move forward. So it's theta naught plus theta naught dot times tf plus a2 tf square plus a3 tf cube. Okay, now let's talk about velocity. So theta f dot is equal to theta naught dot plus 2 a2 tf, right, when we differentiate, and 3a3 tf square. Okay, this is what we'll have. From here we have to solve for a2 and a3. So we have one equation here and the other equation here. Okay, we have to find out a2 and a3 from all these equations, because we already, what are the boundary conditions, what all things are known? This is known, theta naught is known, theta naught dot is known, theta f is known, theta f dot is known. All of these four quantities are known. Okay, so what we have to do, we just have to find out what is a2 from here, what is a3 from here. Okay, and I'm not going to calculate it because in the interest of time I won't be calculating, but I'm just writing the expressions in case you are willing to do it. Please do it and check. So a2 should come out to be 3 theta f minus theta naught by tf square minus 2 theta naught dot upon tf minus theta f dot upon tf. Okay, and a3 would come out to be minus 2 theta f minus theta naught upon tf cube plus theta naught dot plus theta f dot upon tf ka square. Okay, so from here what you can do, if you go for cubic polynomial, we get position, velocity and acceleration, all of them to be continuous. Okay, and then we cannot control acceleration at boundaries. Okay. So if you, for example, I give you a numerical problem and I want to, and I ask you to do it, you'll be able to do now, right? Okay. So let's talk about if we have via points. Okay. If we want, so let's go with case one. So let's say the case one is when velocity is given. Okay. So when velocity is given for multiple points, what we can do? We can use multiple cubics. Okay. It is only C1 continuous and acceleration is discontinuous. The other case can be when velocity is not given. Okay, so then you'll have to solve for velocities, and what you'll have to do, you'll have to enforce velocity continuity and acceleration continuity. Okay, so from here you'll get full smooth trajectory. Okay, now if we are supposed to follow Cartesian trajectory, how we are going to do it? Why Cartesian? Because it is very natural for all of us, because we just, if we are supposed to fetch a bottle, we take care of our end effector and we do not plan for our joints, that how our joints are going to move, right? We plan our end effector to reach, we plan our palm to reach a certain position, and in that way whatever action is taken, whatever joint angles, joint velocities are used, that is very natural. Okay, and then we also want to have easier obstacle avoidance. So there can be straight line motion, there can be circular motion, and I think I won't go into details of it because in slides you might have seen that there is a cubic equation for straight line motion, and you can determine, if let's say xt is cubic, you can find out yt zt from the line equation. So you plan one variable and you derive others, right? That is something that has been already covered in straight line motion. Okay, then there can also be circular motion, and here how do we go about it? It is just mathematics. Here you find the plane normal, you define the coordinate frame, you transform the points, you fit a circle, and then plan angle phi using cubic and all of those. Okay, so if you remember, x is equal to a plus r cos phi and y is equal to b plus r sin phi. Okay, so one thing is that it may pass through singularities and you must check the workspace if you are within it. Okay, okay, so after this, okay, single link model, I hope you have already gone through. It basically consists of motors, gears, motor gears and link, right? So your relation for the gears is like this. Okay, where n is the gear ratio, and then for motor, I don't want to write the equations of motion again, but you might have seen jm theta m double dot plus fm theta m theta dot m plus t1 is equal to tm and all these things. Okay, for load also you can write similarly. So if you combine these, I think you'll be able to come up with a single equation. So gear reduces disturbance by a factor n. Okay, so after this there is DC motor model, and again in DC motor, if you have all you know already that in DC motor your torque is directly proportional to current. So there is a torque constant coming in here multiplied by Ia, and from the electrical circuit that you have here, resistance and an inductor. Let's say we do not have inductor, then we can directly take it to be back EMF. Okay, and let's say you are supplying a voltage here, so your VA is equal to RAIA plus kg into theta m, because this is the back EMF that is being generated. Okay, so if you combine everything, you basically get an equation in terms of J capital omega dot plus F omega. These all are constants and I'm not writing the values, but yeah. So this is the core system equation when you combine all the electrical and mechanical circuits, sorry, electrical circuits and the mechanical load together. Okay, so when I am writing this and I'm doing this, are you guys aware of Laplace transform? Have you read about this? Okay. You have asked, is Cartesian space similar to Cartesian plane? Uh, See, it's all about the dimension. When you're talking about, yeah, you can use it interchangeably. It is same. Okay. So, okay, you said that you have heard this Laplace transform. So, can you tell me what is the Laplace transform of x dot? It's a function of t. Do you know the answer? See, you need to know this. You also need to know this. And okay. No, just x's. So for Laplace transform of xt, I think Shravan left the chat. Okay. So I'm putting it on record here. So Laplace transform of xt is xs. Okay. If I talk about Laplace transform of x dot t, it is not just xs, it is s into xs. And with so, okay, Shravan has joined again. Just I was clarifying what is your mistake. So Laplace transform of xt is xs, but Laplace transform of differentiation, when you have differentiation, an extra s term pops up over here. Okay, so it's s into xs, and minus you'll have initial condition terms, but when we take transfer function we ignore the initial condition terms, and x double dot के लिए it would be s square xs. Okay, so this is the very basic Laplace transform that we'll see today as well, and this is the place from where control system starts. Okay, so in our case our omega s upon vas would be k upon js plus f, and this completely comes from Laplace transform. I'm not going into detail, but then I want to cover something which should be very useful to you guys, and I think okay, so there is something called open loop control. Okay, and then there is something called closed loop control, and there is difference between them. Okay, now what it is? In open loop control, for I'll explain to you with an example, and then I'll ask you a few questions for which you can classify open and closed loop. Okay, let's say I have a motor. Okay, let's say this is my motor. I am giving it an input. Let's say my input is some voltage that I'm giving. Okay, and then I want to control the speed. I want it to move at 1500 rpm. Will I be able to do so forever? I mean, if I have a chart which says for 15 volts you will be able to get 60 rpm, but it isn't just open loop. I don't know, there might be many effects coming in. The motor may get heated up, the motor may have some hysteresis developed inside it, or there might be some external noise or disturbance coming in. How would my motor be able to just maintain 1500 rpm? It won't be able to, right? So there should be some error correction mechanism. Let's say if it maintains 1200 rpm and I want it to maintain 1500 rpm, there should be a mechanism by which this error is corrected, right? So what I should do? I should have some sort of measurement of the output, and that output should be taken as feedback, right? So for example, what do we do then? We will have again voltage coming over here. Okay, and this would be motor again. Okay, it's the same thing. And then we have the output. Let's say our output is speed, which is n. Let's say I have a measurement device called tachometer, okay, which measures the speed of my motor. Okay, I take it as a feedback. So what I do? I will have a reference. Let's say my reference is 1500 rpm, which I want to maintain. I am okay. So let me draw this properly, else it would be very confusing. Okay. So this goes in plus. Okay. Then I have the feedback, which is this. Okay. Both of these combined give me error. Let's say I am getting the speed to be 1200 rpm currently. Okay, so if I subtract 1500 minus 1200, I get an error of plus 300. Now I need to take some corrective action based on this 300 ka error. So I need to have a controller. Okay, some controller is basically some gain will be there that might be multiplied with my error, so that a proportional voltage is produced that corrects this. So maybe next time it would not be 1200 but it would be 1300. So again I see that I have an error of 200 and I should take the corrective action accordingly. With this, a point of time will come when I'll be able to settle at what I wanted, whatever was my desired speed. Right, I'll settle at that particular speed. Now, the control system has a certain has a number of performance parameters. For example, how fast you are able to settle down. That is called settling time. How fast are you able to reach the so for example, I should draw this. So let's say this is my time and this is the value that I want to achieve. Let's say it is 1. Okay, so if my response is like this, okay, so I had to achieve this 1 point, but what happened? I my controller worked in such a way that it overshot the value. There is some overshoot coming in, and then it settled down the oscillations, it damped, and it finally converged to the steady state value. Okay, so you see the error is decreasing over the time. I wanted this one to be maintained, it is happening, but it is taking some time, and the error is decreasing. Why? Because the controller is acting on it. Okay, now this this thing is called maximum peak overshoot. How much overshoot did I have when as compared to what I wanted to have? Okay, this time up until here, this time is called rise time. Rise time means the amount of time it took to hit the desired value for the first time. That means kitna jaldi I was first able to hit the value. It shouldn't be that my response is rising like this very slowly, and sometime it would hit. No, it has hit here. Okay. So this is rise time. Okay. Then there is something called settling time. Now settling time, you might not always be able to achieve the desired value, which is 1. You might be somewhat 0.99999. That does not mean that you haven't settled. You have settled, but there is a very small steady state error. Okay, so what I need to do, I need to quantify this as well. So I would say my settling time comes in 2% of the band or 5% of the band. So both are the ways in which settling time is defined. Okay, so if I am in 2% of the band at some point of time, okay, then what is the time that I have taken to reach within 2% of the band? That is defined by settling time. Okay, then we are also concerned about peak time. At what point of time this peak appeared? Okay, that is called peak time. This particular time is peak time. Okay, so what essentially happens here is these are the performance indicators of a second order system. All right, so when you saw the first order system response, I hope you might have seen this kind of response where it reaches the steady state value, right? And when you saw the second order response, it looks like this. And you might have already seen the transfer function corresponding to this, which is something output upon input. It's just that is a transfer function of the system is basically omega n square upon s square plus 2 zeta omega ns plus omega n square. Okay, so this omega n is called the natural frequency. Okay, and this zeta is just a damping ratio. So based on the value of zeta, you basically can find out what is the damping of the system. For example, you might have seen the door that closes automatically, right? Now, so I want to just show you a relationship between zeta and maximum peak overshoot that you can see in your real life. You don't need to study control system. Okay, so if there is a door that closes on its own, okay, I am no, sorry, I want to show the relation between zeta and rise time. Okay, so if let's say my door is like, I have opened a door. Okay, I have opened a door. Okay, I have left it open for some time, and now I am leaving it and it is closing now. Let's say damping is very high. ठीक है, बहुत हाई डैम्पिंग होगी तो क्या होगा? Would it settle faster or slower? Damping is very high means I don't want my system to overshoot. I think I want to compare it with this only. So let's say I want to reach this value. Okay, I want my door to become closed now. But I am taking, so if I have higher damping, what would happen? I would, what would the door do? The door would slowly go to the desired value. It would take a lot of time, and it would reach the desired value. Right. But if my damping is really low, what would happen? If my damping is really low, then my door will go back to its original position, overshoot in the other direction, come back, overshoot in the same direction, and go back. I mean, there would be oscillations. It won't settle down immediately. But if I have a highly damped system, there won't be any overshoot. But the system response would be very slower. So there is a trade-off always between the damping and maximum peak overshoot. If you increase the damping of the if you increase the damping of the system, then you will have less overshoot. If you uh, decrease the damping of the system, your system will have more overshoot. Okay. So if you study the formula, then also it is maximum peak overshoot is minus e to the power minus zeta pi upon under root 1 minus zeta square. Okay. So this is the way how it is defined. And this is a very important, very important transfer function of second order system. So from here we basically find out what are the poles of the system, what are the zeros of the system. They basically mean where do the roots of the denominator lie, they are called poles. Where the roots of the numerator lie, they are called zeros. And if all the poles lie in the left half of the S-plane, because this is only defined for transfer function, it has nothing to do with time domain. So for example, I give you a transfer function S upon S plus 1 into S plus 2. Let's say this is my system. Okay, I am denoting my system by GS. So where are my poles and zeros? My pole is at minus 1, another pole is at minus 2, and my zero is at 0. Right? So all my poles, and this is S-plane. Okay, that is why my roots are minus 1, minus 2 and 0. So all the poles lie in the left half of the S-plane. That means that the system is stable. Okay, if any pole, a single pole, let's say there are 5 poles of the system, all 4 of them are lying in the left half of the S-plane, but one of them is lying in the right half of the S-plane, that makes the system unstable. Okay, so this is all about this control system. Okay, settling time you have already seen. Settling time is defined by 4 upon zeta omega n. Okay, so what I was talking about here, that the time it takes to reach within 2% is the settling time, and it is given by 4 upon zeta omega n. And all of these are not empirical, they all are derived completely from the differential equations of second order system. Okay, it's not ki this has been found or this has been experimentally validated for a number of systems and hence this exists. No, it's derived. Okay, now one thing which is very important that you might have seen is PID control. Can you tell me something about PID control? Okay, so your question is which controller is best for robot? The very first controller that you should always start with is PID control. Without a chance. This is the basic form of control. This is highly easily implementable control method. You just have to tune three values and you'll most likely be able to control your robot. It's just that there are some rules that you should follow, that when I have to tune which what do we say, which gain, when I have to tune which gain. For example, for PID controller there are KP, KI and KD. So you basically have to tune them and you need to know the significance, that when which one has to be tuned, and then you will be able to use the correct controller, use the get the correct or the desired response. There are many other controllers as well. Okay, all those controllers that you can use, for example, you can use many non-linear methods of control. Okay, then there is something called optimal control, there is something called adaptive control. So there are a number of controllers available, but all of them are what do we say, I mean, it depends. If you need that, then only you need to use it, and it is not really a very basic mode of control. Like, you need to understand if your system at all needs this. But the very first control that you should always try is PID control. And for a simple system, a simple robotic system, it actually helps every time. Okay, the challenge is, how do you tune these? That's it. Okay, so what is a PID controller? So let's say my error. So if you remember this diagram, there is a reference value, there is a output coming from sensor. This is a reference value. There is an output coming from sensor, and we are getting an error. That error is being processed through the controller to obtain what should be the desired voltage, right? So if my VA, let's say I operate the controller on the error, and this is the output that I get from the controller. So I do KP into the error itself. KP is a single constant. Okay. Then I do KV. I don't use KV, by the way. KD into E dot, derivative of the error, and KI into integral of the error. Okay, so these terms are responsible basically to drive me to the desired position. I'm taking into account what is the current error and I'm acting on it. I'm taking into account how the error is changing. That helps me get a sense of noise. Okay, and this tells me how much error is accumulating over the time and how should I take the corrective action. Okay, so basically your in PID controller, P reduces the error. Okay, I removes steady state error, and D reduces the oscillation. So when you apply the controller and you find any of these things happening, you will understand which constant you need to tune. So PD basically controls the dynamics of the system, PI removes the steady state error, and PID does both of them. Okay, so so just hold on. I think this much is sufficient, but okay, I hope you have understood this closed loop and open loop system. So in control, what do we actually want? That the output should follow the desired input. Okay, so a control system ensures that a system behaves the way we want. The robot should behave the way we want. If we want a particular joint to move at 45 degrees, it should be able to move. Okay, and should be correct enough. Now correctness depends also on the resolution of the sensor. your sensor is going to give you a feedback that what is the error or what is the current reading, and then you find out the error. Okay, so if I ask you a question, is temperature control an open loop control or closed loop control, what would your answer be? I mean, I'm just asking about. Okay, so is AC, air conditioner that we have, an example of open loop control or closed loop control? Okay, you say closed loop, and why do you think so? Do you have any reasoning, or should I say the answer? I mean, you can give it a try. If you want to unmute yourself, that is also perfectly fine. I don't know if I'm able to understand clearly by what you've written. Hmm. That is right. It minimizes. Okay, yeah, right. Very good. So sensor is coming into play there. It measures the actual temperature. It gives a feedback on the temperature of the room. Right. It yeah, you have written correctly. It adjusts a compressor to correct any errors. So it takes into feedback the temperature of the room. It calculates the error. It runs a controller. The controller takes the corrective action. It supplies or more than supply. So there is something called bang controller. Okay, bang controller, which is basically on off control. The controller manages all of this. The controller is a entity that is just programmed. It is not something different. 8 बजे तक बुक किया है 8 बजे तक लिखा हुआ होगा बाहर बुक किया है so yeah what I was saying is कि the controller actually yeah there is a controller and controller is not a different part, it is not a hardware, it is just a program that you have to apply to the errors coming in. Okay, it is not a different part. Okay, so here this bang is on off control that is used in ACs generally, and it is like temperature का difference अभी आ गया है, let's turn on the AC or let's turn off the AC. Okay, it is a very simple control. Whereas if we talk about washing machines, do you think there is a closed loop control there? There is a closed loop control, but actually there is no closed loop control in washing machine. The reason is you set your washing, they have more error. No, they have more error and no one is taking into account. That is a problem. So why I'm saying this, I'll tell you. So when you, yeah, it is open loop control, sorry. So when you uh, put your clothes to dry in the washing machine or to wash, let's say you set the timer to 1 hour, that for 1 hour the cloth has to be dried. If in case your cloth is this washed and dried, both of them happen before 1 hour, your machine is not going to tell you that it has washed here, your clothes are clean now, and now you do not need to wash it or rinse it any further by spinning. Right? You set it for 1 hour, it will go on working for 1 hour. It's you who decides. It does not have any sensor based on how the things are working, whether everything has been reached, or whether it has made some certain number of rotations, or there is no such thing. You don't get any feedback. What feedback you have visual feedback. That's it. Okay, so the washing machine is an example of open loop system. For example, for the same reason, if you also talk about the fans, they're also an example of open loop system. Why? Because you have a regulator, you choose between 1 2 3 4 5, your fan speed changes, but it is not always fixed. Like sometimes it might move at 200 rpm, sometimes it moves at different rpm. So there is no one to take the sensor reading and then correct it. Even if it is moving at more or less speed, it will move. Okay, so it is also an example of open loop control. Okay. Okay, so another example is toaster. You don't know if your bread has been baked or not, right? That also comes from your visual feedback and from your experience. So it's a problem. Wherever there is a feedback, it is closed loop control. Okay, and error basically drives the control action. Feedback is important because it helps in improving the robustness and accuracy. Okay, now Laplace transform you already know very clearly. So uh, let's say the I take an example of mass spring damper system. So if you know, it is given directly by this equation where Ft is any external force acting on it. Okay, and B and K are damping coefficients, and uh, this is what is this term called? K into X. Just let me check. It represents a restoring force. That is what I was thinking. Okay, so it is just the restoring force where the K is the spring constant. Okay, so if we want to write the transfer function of this differential equation to the second order differential equation, right? So it would be m s square xs plus b s xs plus k into xs is equal to fs, right? From here, if I want to find out what is xs upon fs, which is transfer function, because your x is the output and f is the force that is going to the system internally. So it is basically ms square plus bs plus k. So this thing is called transfer function. And make sure when you are converting into Laplace for this differential equation, you cannot take any initial conditions into account. All right. So this is transfer function. So you have to ignore the initial condition only when you're writing the transfer function, not when you're solving these equations. All right. Okay. If I talk about first order system, The general transfer function is given by 1 upon tau s plus 1, where tau is the time constant. And what is the time constant? That is something that you should read out. And if you, so this is basically equal to ys upon rs. So your yt is essentially 1 minus e to the power minus t by tau. This comes after you solve it for a step input. Okay, only if your rs is a step input. Step input means it is 0 here, and then at t is equal to 0 it switches to 1. So your for this the Laplace transform is 1 upon s. Okay, so I'm not going into detail. So time constant is defined when the it is the time when output reaches 63%, the steady state value. Okay, what would happen if your tau is increasing? That means the output is able to achieve 63% at much later point of time. That means that the system is a slower system. Okay, now as we talked about second order system, right? So here what we said that our transfer function is given by omega n square upon s square plus 2 zeta omega n s plus omega n square. From here we said that omega n is the frequency, natural frequency of the system, and zeta is the damping of the system. So there are a number of cases that you should know. If zeta lies in between 0 and 1, it is an example of underdamped system. Underdamped means it would oscillate a lot. It is going to oscillate a lot and then come back. If your zeta is equal to 1, it is critically damped. Critically means it would just achieve this value. And if your zeta is greater than 1, means it is over damped. This damping was not required, so it would be a very slow system to reach the steady state value. All right, so for underdamped systems the oscillation is there, overshoot is there. For critical it is fastest without the oscillation, and for overdamped it is the slow method. Okay, so after this you already know what is settling time. I have already told you it is 4 upon zeta omega n, and maximum peak overshoot is e to the power minus zeta upon under root zeta pi upon 1 this thing. Okay, these formulas are extremely important for dealing with control systems in robotics. Okay, now, if we talk about the system, as I said, that the poles of the system should lie in the left half of the S-plane. So, if you find out the roots of this equation, if they lie in the left half of the S-plane, that means that the system is stable. If it is in the right half of the S-plane, the system is unstable. If it is on the imaginary axis, then it is marginally stable. Marginally stable means for certain inputs the output may explode. By explode we mean that it may reach infinity and the system may not remain bounded. You might have a response rising and growing all of the times. So that means exponential growth would happen on the output side. You are giving just a simple input, let's say a step input, but your output is always growing. So that is an example of unstable system. Okay, now about PID controller also, I made clear that there is a proportional controller which reduces the error, and it is responsible for reducing the error and for fast response. Okay, then derivative basically reduces the overshoot and predicts the future. It is called anticipatory controller. Okay, and integral basically removes the or reduces the steady state error. Okay, so if you have large ki, it might lead to instability because you might try to decrease the steady state error, but large ki does not help. The system is not going to achieve at all. And large kd means that it is noise sensitive, it is sensitive to noise. Okay, so I think all of this is clear to you. We can move ahead with a few questions. Okay, I had to solve a few subjective questions, but I think We can do it at the end. Let's start with objective questions first. Okay. So a piecewise cubic trajectory in joint space through k via points has k segments each with C2 continuity, has k plus 1 segments each with C2 continuity, can have C2 continuity over the full trajectory if velocities at the via points are not specified, can have C3 continuity. Okay. So if you have k via points, okay, if you have k via points, your total points are initial plus final plus k via points, right? So it is basically k plus 2 points. So then if there are k plus 2 points, the number of segments that you're going to have is k plus 1. So this option is correct, right? And with this we can discard the first option. Okay, so option 1 is has k segments, which is wrong because with k via points you divide a trajectory into k plus 1 segments and not k. So this is just a counting trap. The second option is each segment is a cubic polynomial. So cubic ensures theta, theta dot and theta double dot are continuous within the segment. So each segment individually is C2 continuous. Okay. The third option is can have C2 continuity over full trajectory. Velocities are not specified. Okay. So there are two cases for which we can check it. So one case is the velocities. So we discussed both of these cases, right? One case is that velocities are given at via points. So in that case, only uh, position and velocity is matched and acceleration is not matched. So it is not C2 globally. But the other case is velocities are not given. You solve for velocities, you enforce velocity continuity, acceleration continuity, and entire trajectory becomes C2. So it can have C2 continuity or the full trajectory. Velocities at the via points are not specified. If it is specified, it is not possible. Okay, because acceleration would not be matched. So it is not C2 globally. The fourth option is it can have C3 continuity. So there is a cubic polynomial, the third derivative, which is theta triple dot is a constant, right? So at segment boundaries, the third derivative is not continuous. Only two derivatives are continuous, which is theta dot and theta double dot. So since it is not continuous, so it cannot be C3 continuous. Okay. So just for your remembering, I'm telling this to you. Cubic has C2 continuity max. Okay. And uh, quintic polynomial, which is the fourth order, has C3 continuity max. Okay. Not any more than this. Okay. Okay. Let's move to the next question. The motion planning for orientation of the end effector is performed using piecewise straight line segments, using piecewise circular arcs, using the Euler angle of the end effector, using the Euler parameters to represent the orientation of the end effector. Okay. So we want to know how the motion planning of orientation of the end effector is performed. So the core idea here is motion planning for position and orientation are fundamentally different. So quantity and representation. Okay. So if I talk about position and orientation, so here in position x, y and z are in Euclidean space. Okay. And for rotation you need special representation. So The first option is using piecewise straight line segments. It is wrong because straight lines are not for position planning in Cartesian space. Orientation is non-linear. It belongs to rotation space. So rotations do not lie in Euclidean space. Right? So it is not correct. The second, this has major problem with rotation. Second problem is the second option is using piecewise circular arcs. Circular arcs are also used for position paths. Orientation is not handled like geometric curves in R3. So this is also wrong. Let's check option 3. Using the Euler angles of the end effector. So Euler angles have some problem of singularity, which is called gimbal lock. They have non-linear interpolation issues. They are not smooth for trajectory planning, so they are not preferred in motion planning. Okay. The fourth option is using the Euler parameters to represent the orientation of the end effector. So these Euler parameters are quaternions. Okay. If you don't know, you need to read about this. Okay. So when angles fail, quaternions prevail. Okay. So it is the, so the thing is, the advantages that we have from these quaternions, that they avoid singularity. Okay. Then there can be smooth interpolation, and they are well suited for control and planning. Okay. So epsilon 1 square plus epsilon 2 square plus epsilon 3 square plus epsilon 4 square is equal to 1. Orientation lies on a unit sphere. Okay. So best way to represent orientation, the answer is always these quaternions. So okay, I think it is clear. Let's move to the next question. Feedback control in a robot is used to follow any desired trajectory exactly in 3D space, in the workspace exactly, in the workspace with desired accuracy in spite of the external disturbances without any changes in the internal parameters, in the workspace with desired accuracy in spite of external disturbances and internal parameter change. Okay. So the core idea is feedback control is not about perfection. It is about robustness. Okay. So feedback essentially what does feedback do? It reduces effect of disturbances and uncertainties. Okay. So the first option is exactly in 3D space. Feedback control in a robot is used to follow any desired trajectory in exactly in a 3D space. It is wrong because real systems always have noise, they have disturbances, they have modeling errors. So exact tracking is impossible. Okay. So it is never exact. The second option is in the workspace exactly. It is also wrong. Same reason. Exact tracking is unrealistic. So it is not correct. You cannot do anything exactly. The next option is in the workspace with desired accuracy in spite of external disturbances without any changes in the internal parameters. Internal parameters do change. Mass changes, friction changes, temperature effects are there. Feedback is specifically used because of parameter change. So this is also incorrect. The fourth option is with desired accuracy in spite of external disturbances and internal parameter change. Yeah. So Feedback control handles external disturbances, like if there is some load torque. It handles internal variations, like parameter uncertainty. It ensures acceptable accuracy and not perfection. All right, so this is the correct answer. So if the options contained exactly, we do not have to fall for it. We have to have desired accuracy and we need to be robust to disturbances. All right, so this is the correct answer. Okay, let's move to the next question. A single link of a robot driven by DC servo motor can be reasonably accurately modeled with a first order linear ordinary differential equation for speed control, second order linear ordinary differential equation for speed. I think this is directly from the lecture and there is no issue to it. So second order linear ordinary differential equation for position control and first order linear ordinary differential equation for position control. Okay, so if the same system behaves differently depending on what you control, and that you've already seen. So control type and system order. If my control is speed, that means I want to control this, then my system is first order. Okay, if I want to control the position, which is theta, then it is second order. Okay, so if we start with motor dynamics, if you remember, it's j omega dot plus f omega is equal to k into va plus td. Okay, so this is a first order ODE in omega. So if for speed control, here omega is equal to theta dot and the equation is j omega dot plus f omega is equal to kVA. This is first order differential equation. Okay, so speed control is first order differential equation. All right, now for position control, your omega is equal to theta dot. So you can substitute j theta double dot plus f theta dot is equal to kVA. This is second order ODE. So position control is a second order system. All right, so these both are incorrect. The first option said first order for speed control. This is directly from the motor equation. The second option is wrong because speed equation has only first derivative. And the third option is definitely correct. And the fourth option says for position always leads to second order dynamics, which is wrong. So sorry, it says first order for position control, which is wrong. So if you want to control the speed, you have to go for first order. If you want to control the position, you have to go for second order. Okay. So in general, the industries prefer speed control loops internally because it is easier to stabilize because it is first order. And then outer loop handles the position. Inner loop corrects the velocity. Okay. Okay. Let's move to the next question. Just hold on. Okay. Yeah, the transfer function between the between the input voltage VA and the output rotation theta for a single link manipulator is where J, F are the equivalent inertia and equivalent friction of the single link manipulator system. K is a constant derived from torque constant and resistance in the coils of the DC servo motor, and Kp is the proportional gain. So we basically want to find out the transfer function. Again, this is directly from the lecture. So if I start with motor equation, okay, j omega dot plus f omega is equal to kVA. Okay, if you take the Laplace transform, it's Js omega s plus f omega s is equal to k VAS. From here, write omega s into Js plus f is equal to k into VA of s. Okay. Now, transfer function for speed, omega s upon VAS is equal to k upon Js plus f. Okay. So, now we need position theta s and not speed. So, omega s is equal to s into theta s. Okay. If you substitute, s into theta s is k upon Js plus f into VAS. Okay. So, in final you get theta s upon VAS is equal to k upon s into Js plus f. Okay. So, the first option which is here is k upon Js plus f. This is speed transfer function and not position. It is missing 1 by s integrations term. So, it is incorrect. Second option is correct. This is what we derived. Third option is also incorrect because this is closed loop transfer function. Question asked just open loop transfer function, so it is incorrect. And the fourth one is it is missing the motor speed, missing motor constant k, and it is also only speed related. So this is also wrong. Okay. So I think it is clear. So just I'm writing it down again. That for speed we had k upon Js plus f transfer function, and for position we have k upon we have k upon Js plus f multiplied by s. Right. I hope this is clear. Okay, let's move to the next question. In a first order system with proportional control, the output for a unit step input is a linear function of time, a quadratic function of time, is an exponential function of time which can exceed 1, is an exponential function of time which asymptotically approaches 1. Okay. So, this is a very fundamental first order system behavior. Okay. So, for a first order system with proportional control, the standard transfer function is gs is equal to 1 upon tau s plus 1. We already saw this, right? So, for unit step input, your rs is equal to 1 upon s. Okay. What is your output? Your output is ys, which is 1 upon s into, because this is equal to ys upon rs, right? So it is 1 by s into tau s plus 1. Okay. So from here, if you take the Laplace inverse, what you'll get it to be equal to 1 minus e power minus t by tau. It is just you have to take this to partial fraction. You have to simplify it in such a way that you can take the Laplace inverse easily. It would be a upon s plus b upon tau s plus 1, and you'll get this as directly the Laplace transform, inverse Laplace. Okay. So there are some key properties of this response. If you see that it starts at 0, like when t is equal to 0, it is 1 minus 1, so it is 0. It increases smoothly. Okay. It never overshoots. You'll never see it rising above 1, and it approaches 1 asymptotically. Okay. So the first option is the output with a unit step input is a linear function of time. It is wrong. Linear means straight line. Actual response is an exponential curve, so it is wrong. The second option is it is a quadratic function of time. It is also wrong because quadratic is a parabola kind of thing, and then it is not applicable here. The third option is exponential, which can exceed 1. No, first order system has no overshoot. It is always, yt is always less than 1 for all time. Okay, so this is also wrong. Fourth option is an exponent function of time which is which asymptotically approaches 1. This is correct because our response was y to the power minus e. Okay, this was there. So as t tends to infinity, our yt tends to 1. So this is correct. Okay, so for first order system there are no oscillations, there is no overshoot, and it is always exponential. Okay, and it is smooth exponential. If there is an overshoot, you think of it as second order system. If it is just an exponential rise, it's a first order system. All right. Okay, let's move to the next question. In a second order system with proportional control, the nature of the output for a unit step input depends only on the input voltage, is oscillatory if the damping coefficient is less than 1, is exponential if the damping coefficient is greater than 1. It depends on the proportional gain in the controller. So for second order system, theta s upon theta ds, this is desired and this is actual. Okay, this is equal to omega n square plus s square 2 zeta omega n s plus omega n square. Okay, we know that zeta is the damping ratio and omega n is the natural frequency. Okay, so the first option is it depends only on the input voltage. No, right? Output depends on system parameters which we have here, controller gains and damping, so all of these, and it's not just input, so it is wrong. The second option is it is oscillatory if damping is less than 1. So if zeta lies in between 0 and 1, it is an example of underdamped system. Means oscillations would be there. So this is correct. Option 3 is exponential if damping is greater than 1. So if your zeta is greater than 1, this is an example of overdamped system. Okay, so no oscillation is there and response is just a sum of exponentials. Okay, the fourth option is depends on the proportional gain in the controller. So if you can directly refer to lecture for this. So you might have seen that there we get omega n to be equal to k into kp upon j, and from there it's a zeta. We were just using a proportional controller there, right? Zeta is f upon 2 j k kp. So changing kp changes omega n, changes zeta. Therefore it changes the system behavior. That is why this is also correct. Okay, the most important point in this question is you need to remember when it is underdamped system, when it is critically damped system, when it is overdamped system, when it is completely oscillatory. So all of these. So damping decides the shape, gain decides the damping of the system. Okay. Okay, so it's not that only damping matters, but controller gains affect damping. Okay. Okay, let's move to the next question. The main effect of the integral term in a PID controller is removing steady state error. I think this should always strike you right away. Okay, removing peak overshoot, making the system more stable, making the system more damped. No. So we know that in PID controller, the output of the PID controller is basically Kp into Et plus Kd into E dot T plus Ki into integral of Et dt. Okay, so the role of integral term is basically so integral error keeps accumulating. If the error is there, control input increases and it forces the error to 0. So integral action eliminates the steady state error. Okay, so this is the first option. The second option is removing peak overshoot. Overshoot is handled by D term. Okay, integral can actually increase the overshoot. Okay, third option is making the system more stable. It is wrong because integral term can cause oscillations. It can make the system unstable. So it does not make the system stable. So this is also incorrect. And the fourth option is making the system more damped. So damping is controlled by the derivative term Kd. Integral reduces the damping. It can cause oscillations. Okay. So the thing is, you just have to remember, if you want to eliminate the steady state error, I is the perfect thing. If you want to damp the oscillation, D is the perfect thing. Okay. And without I, there would always be steady state error. Okay. So integral forces system to keep the error until error is, to keep correcting until the error is 0. Okay. I hope this question is clear. Okay. Let's move to the next question. Analysis and design of modern robot controllers is based on S-domain approach, based on the use of Z transforms. Is possible only in time domain, involve analytical solution of ordinary differential equation. Okay, so modern robot controllers are digital, implemented using microprocessors, work in discrete time. So continuous time is S domain. Okay, this is important. Continuous time is S domain and it is Laplace domain. Okay, discrete time is Z domain. So the first option is it is based on S domain approach. It is wrong because S domain is continuous system. Modern controllers are mostly of digital type. So S domain is mainly for analysis and not implementation. So this is wrong. The second option is it is based on the use of Z transforms. This is correct because this is what that happens in digital control. Okay. Digital control involves sampling. We use dz. Okay. And Z transform is discrete equivalent of Laplace. Okay. The third option is it is possible only in time domain. Design is not restricted to time domain. Frequency and Z domain are heavily used. Okay. And the fourth option is it involves analytical solution of the ODEs. So it is wrong because modern control uses numerical methods, discrete updates, no need for analytical ODEs. Okay, so this is also wrong. Sorry. So we just have this as the correct answer. These are the wrong answers. So modern digital controller, you think of it as Z transform. Classical control used S domain. Okay, so the real robot sample data at 1 to 10 milliseconds. Control is computed at discrete instance. Okay, now this is the final question that we'll be dealing with today. Given that the voltage applied to DC servo motor is plus minus 12 volts and the 12-bit ADC analog digital converter is used, the least value of voltage that can be applied is what millivolt. So this is a numerical concept question on ADC resolution. Okay. So what we are saying, the voltage range is plus minus 12 volts. Okay. And our ADC is 12 bit. So total, what is the total voltage range? Total voltage range is plus 12 minus minus 12, which is 24 volts. Okay. And what are the number of levels of ADC? Let's talk about this. So for 12 bit ADC, 2 to the power, that means 4096 levels are there, right? So we want to know what is the least voltage that we can get. So we'll find out the resolution, which means least voltage, and the resolution is given by total range upon number of levels. Okay, so the total range that we calculated is 12 and the total levels is 4096. From here you can get it to be equal to 0.586 volts nearly. If you convert this to millivolt, it would be 5.86 millivolt. Okay, so your final answer that you'll have here is 5.86 millivolt. Okay, yeah, it might be that you might not get the same numerical answer, but anything in between 5.7 to 6 can be accepted. Okay, so what you just have to remember, this was really important, that your resolution is always, sorry, your resolution is always range upon 2 to the power n. Okay, if there are more number of bits, that means that there is finer resolution. Okay, also the question had plus minus 12 volt. Students usually forget this minus sign and they don't take out the range, so they usually take just 12 volt. No, it is 24 volt range. Okay, so you have to use 24. So the whole calculation was 24 upon 4096. Okay, if you approximated by 4000, you will immediately get it to be equal to 0.006 millivolt. All right, so in the next class we'll see non-linear control of robots. So today we saw the linear controller. PID is an example of linear controller. We'll see non-linear control of robots, where we'll learn how to control a multi-link manipulator, and how do we control the constraint and parallel manipulator, Cartesian control of serial manipulators, etc. Then what is called the force control of manipulators, what is hybrid position force control of manipulators. Then there would be some topics in non-linear control of manipulators. Okay, so this is what we'll be doing. So next lecture also deals with control. Today it was linear control, next time it is non-linear control, and then we'll switch gears and move to wheeled mobile robots. There we'll see a number of things. How does it move on flat terrain and on uneven terrain, and how do we derive the kinematics and dynamics of this wheeled mobile robot, etc. Okay, and then we'll see over constraint mechanism in the last part. That's okay, but we just have 3 lectures due after today's lecture, and I request, the attendance here is very low. I am putting it on purpose so that it gets recorded and then it can be watched. So the thing is, please attend the classes, clarify all your doubts, because your exams are near and I know you need to appear for it. So clarify all your doubts in the last 3 sessions, and next time we'll deal with this nonlinear control of robots. So we are done with today's lecture. If you have any question, you can tell me. Okay, I guess there are no questions. So thank you for attending the today's session. We will meet next Monday at 6 p.m. Uh, Same time, same link. We'll meet next Monday. Okay. Thank you. Bye.
Okay, ma'am. Good night.
Sure.